Welcome to the second video in this series discussing the Walnut software. Walnut is the controlling software used in the FPath project, and in order to have enough context to really understand this video, you need to have previously viewed part 1. There is a link to that video and the FPath project in the description below. Let's go step by step through the system described in the first video. Before we get into the details, please be aware that I have been working towards creating the Walnut software for quite some time. Most of the components of the Walnut software are bolted together from software modules in other projects I've created. You're going to hear a number of project names. Please don't think I am trying to promote these projects. The functionality they provide is used extensively in the Walnut software, and I need to document that fact. Also, please note that there is simply not enough time to describe the workings of all these modules in any detail. All of the modules have their own write-ups and standalone demonstration projects. Links for each project are located below in the video description. Just click on those if you'd like more information. Sorry about the digression. Let's get back to the point. Let's review the system discussed in the previous video. We have a PC which accepts a stream of data from a USB camera. The fact that the communication is via USB is helpful because later on, as we go smaller, we can just substitute in a USB microscope for the camera and the system will still work. The Walnut server software running on the PC is written in C#. The image processing substrate is Windows Media Foundation. Let's call that WMF for short. This was derived from code in the Tanta project. WMF provides the ability to accept a stream of video from a USB source and display it on the screen. It can optionally also record that stream to disk as an MP4 file. What is more, the Tanta project code in the Walnut server software can interpret the contents of the video stream as it passes through the system. WMF has a software structure called transforms, which are little bits of user-written code you can place inline in the video stream in order to operate on each frame. The type of things you can do are endless. For example, you could write text over the top of the video stream, invert it upside down, change the color to monochrome, split the stream into two, and so on. All of this is done up in the user space in C#. You can run the debugger over the code, and you can pretty much do anything to the video stream you can think of. In the case of the Walnut server software, there is a transform in place which provides inline real-time image recognition on the image stream. This image recognition is provided by integrating an open-source image recognition tool called EMGUCV into the transform. The basics of using EMGUCV in C# can be found in the Prism project. So, the fundamentals of the Prism project have been incorporated into a WMF transform, and this provides the ability to recognize circles and squares in the image stream. Without going too much into the details, ultimately, what happens is that a list of circular objects, square objects, their colors, and their center pixel coordinates are continuously discovered and presented to the main Walnut server processing engine. Reflecting back on the discussion in part 1 about closed-loop control, you can see how having such a clean list makes it much easier for the Walnut software running on the PC to make decisions about what to do. If the controls on the front panel of the Walnut software indicate that the red square should be moved on to the green square's location, then commands to that effect can be prepared. The primary function of the Walnut server software running on the PC is to interpret the images coming off the USB camera and make overall decisions about what is going to happen. Low-level control operations, such as figuring out how to achieve the desired effects, are left up to the Walnut client software running on the Beaglebone Black. Here is the Beaglebone Black. It is connected to the PC via a Cat5 Ethernet cable running TCP/IP. The Beaglebone Black runs a full version of Linux. All of the standard Linux-based tools are available and operational on that platform. The Walnut client software on the Beaglebone Black is also written in C#. Yes, C# runs very well on Linux, much faster than other bytecode-based languages such as Python. So how does the information get transmitted from the Walnut server to the client? Well, you can make up all sorts of protocols to manage this transfer, but since both software programs are running C# and can share code libraries, by far the most ideal way to transmit information would be to stuff an instantiated and fully populated .NET object into the pipe at one end and have it appear at the other end as an identical, fully instantiated and populated .NET object. Fortunately, I have written a demonstrator project called RemCon, to do just that. Both the Walnut server and client incorporate code from RemCon. Everything is transparent to the applications. They just give the object to the RemCon library and it magically appears at the far end as that same object. Interestingly, it works in both directions. The Walnut client on the Beaglebone Black can create an object containing whatever information it wishes, and it will automatically appear on the Walnut server on the PC. This makes it easy to provide additional feedback into the software on the PC. So that takes care of the mechanics of the data transmission, but what gets transmitted and what happens when it arrives? Well, the Walnut software project is open-ended and changes constantly. At the moment, all that happens is that the Walnut server software sends the locations of the first red square and the first green square it sees, along with a command that says, move red onto green. Inside the Walnut client software, there are subroutines called action modules and behavior modules. Action modules interpret the incoming command and pass the data into the appropriate behavior modules, which then interpret the data, red and green square locations for example, and generate simple things like the speed and direction values that will ultimately control the motors. The important thing is that the behavior models are not stateless. They are aware of what they have previously output. This makes it possible for them to do things like adjust their output, slow down or speed up, based on how fast they are approaching the desired target. In other words, PID control is possible. The action and behavior modules, as currently implemented, are not terribly sophisticated. However, they are intended to act as replaceable units which can be substituted in as required in order to generate specific behaviors. The inputs and outputs of a behavior module are standardized so they can easily be swapped in for one another. The output is an integer number between 0 and 99, which represents a proportion of the speed between min and max, and a Boolean value of 0, 1, which represents a direction. Once the action module gets the output from the behavior module, it can send signals to the motor drivers. If the motor driver is attached to a pulse width modulation port, then the action module can directly activate an appropriate stream of pulses. If the motor is something like a stepper motor, the pulse width modulation port could be used for that as well, since the frequency is also variable. However, the pulse width modulation ports on the Beaglebone Black are limited in number, so the action modules interfacing with stepper motors typically interact with an assembly language program developed for the TILO project, which runs in the Beaglebone Black's programmable real-time units. Let's call them PRUs for short. Explaining the PRUs necessitates another digression. The Beaglebone Black is running Linux, and the Linux version it runs is not real-time. This means that processes can be, and are, swapped in and out of memory in order to give other processes some CPU time. This is not optimal. When controlling machinery, you do not want to have a process suddenly stop sending signals at arbitrary times. You need it to be constantly operational. The usual solution to this problem is to use a dumb microcontroller such as an Arduino or more sophisticated variant. The problem here is that without an operating system like Linux, you lose a lot of functionality, such as the ability to transmit data easily or to make clever decisions. The Beaglebone Black solves this problem in two ways. Things like the pulse width modulation ports have their own clock. Thus, if they're set to output a waveform of a certain pulse width and frequency, they will continue to do so even if the process that requested it is swapped in and out of memory. The other way that Beaglebone Black solves this problem is with the programmable real-time units, the PRUs. These are essentially mini microcontrollers within the Beaglebone Black itself. There are two of them, and they are very fast, 100 megahertz in fact, and can be programmed in assembly or C. Furthermore, they have access to the address space and I/O ports of the Beaglebone Black, so data can be fed in and out of them, and they can control their environment. The PRUs are absolutely real-time. When they are set running, they execute in parallel with the CPU of the Beaglebone Black, and there is no swapping in and out of memory or pausing their execution. The TILO project assembly code running in the first PRU is designed to accept up to 6 frequency values and output a guaranteed steady waveform for each on an I/O pin. These can control the stepper motors. It does not matter how many motors are running simultaneously or if they are turned on or off. The waveforms are always exact and precise, no matter what happens. There is never a gap, and there is never an extended pulse. So, to return from our digression, if an action module is controlling stepper motors, it just sets a frequency and direction in the PRU. A consistent waveform will be produced on a specific output pin until the PRU is told to stop. The BBB CSIO project handles all of the I/O interfacing with C# and also the interaction of C# with the code running in the PRUs. Here are the motor drivers. The output waveforms, be they pulse width modulated or stepper signals or something else, along with the direction signals, are fed into the appropriate driver module. These generally consist of commercially available driver modules mounted on a custom created PCB. The circuit boards are created with the Line Grinder software, a PCB isolation routing project I have created. Line Grinder easily creates PCBs like that. This saves the time and expense of paying a board house to produce them. Here are the motors. The driver modules convert the signals from the Beaglebone Black into power and are connected to the motors to make them turn. Currently, for DC motors, the DRV8838 from Pololu is used, and for stepper motors, the Pololu DRV8834 is used. Well, that pretty much completes this video. You can see that the Walnut server and client both incorporate components from a number of other projects, all of which were designed to add a particular bit of functionality to the software. Hopefully, this video has provided you with a deeper understanding of how the Walnut server and client software operate and why they are structured the way they are. The next video, part 3, will actually demonstrate the Walnut server and client software.